Hi, MGA. I'm Ellen Kirk, VP of Strategic Marketing for oneNav, a Silicon Valley startup. The last time that much of the oneNav team got together, we put GPS into your cell phone. So please think kindly about us the next time you don't get lost. Today, I'm going to bring you back to a single frequency GNSS world, but show you performance that beats any single frequency results that you've seen before. oneNav has developed a GNSS receiver which uses only signals in the L5 band. GPS L5, Galileo E5A and E5B, Beto B2. All signals at around 1.2 gig. Let me tell you about it. The location market continues to grow beyond today's $5 trillion level, and performance requirements are tightening. As you well know, the GNSS industry has received a significant global modernization over the last decade. These modern signals make it possible to support higher accuracy expectations. Throughout this video, I'll tell you a little bit about oneNav and describe how we've pushed GNSS receiver innovation even further. All four global constellations, as well as both regional constellations, either have upgraded or are in the process of upgrading satellites to broadcast new signals with a common structure in the L5 band. This upgrade is a lot like when cell phones moved from analog to digital. It's a big deal. This once-in-a-generation upgrade comes courtesy of tens of billions of dollars spent by the US, Europe, China, Russia, India, and Japan, all of whom agreed to put the new signals in a protected band designated worldwide for aeronautical navigation. At oneNav, we use L5 as a shorthand for all the L5 band signals broadcast from each of the 6 different constellations. An L5 signal has about twice as much power as L1, carries a lower risk of interference and improved multipath protection, and is easier to acquire in unfavorable and obstructed conditions. L5 codes are both 10 times longer and have a chipping rate 10 times faster than the old L1CA code. Since the maximum resolution available in a pseudo range is typically about 1% of the chipping rate, the faster the chipping rate, the better the resolution. The better the resolution, the better the accuracy. Finally, L5 band signals have much better cross-correlation protection and better narrowband interference protection than L1. The L5 frequency first started showing up in mobile devices in 2020, meaning the engineering had begun several years earlier, before the Galileo and Beto constellations were even fully commercial. Given that timing, it makes sense that incumbents chose to bolt a new L5 receiver onto their existing L1 products. The downside here is that the only way to get to the technological improvements available from L5 is to go through a narrowband L1 signal designed half a century ago. All L5 capable devices on the market today depend on L1 for acquisition, meaning the L5 receiver generally is used only for tracking. What's wrong with this picture besides the fact that it's really complicated? Well, in high multipath environments, L1 performance is dreadful, so getting any fix at all can be challenging and time-consuming. Once the L5 receiver can track, the L1 chain just comes along for the ride, costing extra and taking up space. The system requires 2 antennas, more space, more cost, more complexity. And, as I'll explain in a bit, coax and interference are much more problematic for L1 than for L5. As devices get smaller, cramming in 2 receiver chains and antennas gets a bit problematic. I actually am an endurance athlete, and I'd love an Apple Ultra watch, but I don't know where on my wrist I would put it. As a startup, oneNav had the advantage of starting with a blank sheet of paper. So we created a single frequency receiver that only uses L5 band signals. we developed a machine learning engine to use the additional data available with L5 to mitigate multipath and further improve performance. Finally, full disclosure, we don't make silicon. We deliver the system as an IP core that can be scaled and integrated easily into any platform independent of process node. With over 80 L5 band satellites available, there simply is no need for an L1 receive chain in a mobile device anymore. L5 delivers as good or better performance than a hybrid L1, L5. The materials cost is reduced, and the headaches arising from engineering around coax problems that L1 brings dramatically diminish. oneNav's pure L5 offers better performance and is so much simpler. Why is oneNav the first to develop a GNSS receiver using only L5 band signals? Well, directly acquiring L5 is difficult. The higher chipping rate, the wider bandwidth, and dual sidebands require a lot more processing power. Our hardware team used an architecture not previously used in GNSS and developed a powerful array processor that can do 100 billion calculations per second. Yes, I said 100 billion calculations per second. Assuming assistance data, we can get a first fix in a single second. Compared to legacy GNSS architectures, oneNav's digital IP core is 8 times lower in both silicon area and power. And our machine learning engine keeps getting smarter as we do more and more field testing. Unsurprisingly, our single frequency L5 receiver decisively outperforms even a state-of-the-art single frequency L1 receiver. Testing against the top-selling Samsung Watch 4, oneNav accuracy is 8 times better on average, and 5 times better even at the 95th percentile. But look what happens when we compare the oneNav receiver to a MediaTek L1, L5 hybrid chip on an Iroha board. oneNav has half the error at 95%, while the MediaTek chip uses twice the number of satellites. How is that even possible? How is oneNav's pure L5 more accurate than an L1, L5 hybrid? Remember that the hybrid receiver has to get an L1 fix before it can switch to L5, and it will get L1 fixes until it can decode time. Pure L5 will get to a better fix faster. In poor signal environments, L1 measurements are so poor that even the DOP gain from extra satellites can't overcome the additional measurement error. The L5 correlation vectors allow machine learning corrections from the first fix, while L1, being narrowband, doesn't really have good machine learning possibilities. And the data-rich L5 signals let us differentiate between line of sight and non-line of sight, beginning with a first fix. The bottom line is that a solution using only L5 band signals can get to fine time and thus improved accuracy faster than a hybrid. In the dominant use cases, direct L5 acquisition sensitivity is consistently better than L1 and, by extension, better than a hybrid because a hybrid starts with L1. With good assistance data, L5 sensitivity is about 4.5 dB better. With decent but not great assistance data, L5 can decode time more reliably than L1. And with lousy assistance data, L5 can decode ephemeris more reliably than L1 can. Not only are L5 signals in a protected band, they are far less affected by interference than L1, especially in today's advanced devices. No LTE harmonics affect L5, while band 13 and band 14 harmonics land right into L1, creating interference products. L5 has fewer than half the intermodulation products arising from LTE, Wi-Fi, and Bluetooth in smartphones and smartwatches. Mobile satellite services such as Globalstar and Iridium broadcast less than 50 megahertz from L1, And these MSS radios are beginning to show up in conventional smartphones and smartwatches. Because L5 signals are 10 times wider than L1, any interference is spread 10 times wider, providing more signal or jamming protection. And finally, the L1 neighborhood isn't protected. It's very busy, and it's getting busier. Multipath wreaks havoc on GNSS signals, but L5 band signals have more information to use to identify an actual peak. And by training the neural network within our AI engine, we can create an enormous database to identify multipath signatures. Multipath doesn't care where in the world it is. So training our engine in San Francisco can improve performance in Stockholm or Shanghai. The top chart shows the effect of oneNav's machine learning algorithms at a snapshot or single fix level. And the filtered solution data reflects smoothing of that noisy snapshot data. As an example, you can see that in a deep urban, high multipath environment, the AI engine improves horizontal accuracy with 95% certainty by nearly 30%, from 28 meters to 20 meters. One topic we frequently hear mentioned is the question of whether dropping L1 is even permitted. The answer is yes. The FCC E911 regulations don't even require satellites, much less an L1 signal. The 3GPP standards support all combinations of constellations and bands, L1 and or L5 with or without Galileo, or Galileo on its own, and the same for BDS. If a receiver has L1, fine. If a receiver doesn't have L1, that's fine too. A little bit about the amazing team at oneNav. We have very talented and highly educated engineers, an in-house team and an advisory board with deep subject matter expertise, and a fabulous set of investors who believe in us. L5 band signals are the future. They're modernized and more accurate, which is what the market wants. There's no free space in any device anymore, so a single frequency solution is increasingly necessary. oneNav has figured out how to directly acquire L5 band signals, and we've been at this for more than 3 years. oneNav has the only commercial direct L5 acquisition GNSS solution in today's market, and it's available as an IP core. Competitors are beginning to acknowledge that L5 only is coming. We welcome them to the future.